Then I think the next thing that we should go to is analysis of a system in the reference frame attached to the center of mass. Now we will, in solving the problems in this chapter as well as in the next chapter, which is on rigid body dynamics, sometimes we will try to go to the center of mass frame and then we will try to solve the problem in that frame, because it becomes much easier to see what's happening from that frame. So here I just want to show you 3 or 4 basic results for what happens when you view a system of particles in the center of mass frame. So for that, let me start with the usual XY coordinate system, although I should emphasize that what we are dealing with is actually a XYZ coordinate system. So let's take that XYZ system itself. So maybe we have a 3-dimensional space, we have our x-axis somewhere and we have the y-axis somewhere, and then the z-axis is coming out of the screen, that is this guy. And in this 3-dimensional space we have got some objects. We have got a particle m1 which is at some place r1. So m1 is at a location r1 with respect to the origin here. Then we have maybe some other m2 particle, and I can define the location of m2 with respect to the origin as this this r2 vector perhaps. Then there is some m3 particle. That m3 particle will be somewhere here perhaps, and that m3 particle's location with respect to the same origin will be defined as this vector r3. And then you can have n such masses and such particles, and these particles are at these places r1, r2, r3, and they might not even be stationary, so they might be moving around. So m1 may have a velocity defined by v1, right? So you may have v1 velocity for this particle m1. Then you may have m2 having a velocity v2, and that may be somewhere else like that, so v2. Then m3 may have a velocity defined by, let's say, v3, and so on. So each of these will have a certain location in space, will have a certain velocity, and will also have a certain acceleration. So all those variables can also be defined with these kind of subscripts. So let's say I define the locations of these particles as r1, r2, r3, and so on up to rn, and I define their velocities as v1, v2, v3, and so on vn, and I define their accelerations as a1, a2, a3, and so on, and up to an. And all of these variables are in the ground frame, let's say that, or with respect to this origin here, right? So from the origin of the XYZ coordinate system that you have taken, you have measured all these r1, r2, r3, rn's, and the rate of change of these will give you the velocities, and the rate of change of velocities will give you these accelerations. So all of these are from the viewpoint of this origin. And let us say that for these n masses, somewhere we have the center of mass. So maybe somewhere here is the center of mass of this n particle system. That black dot is the center of mass. The place where the center of mass is maybe just a point in space. There may not be an actual mass present over there, that is besides the point. But then this center of mass will have a location. So maybe I can say this is our center of mass. And as these individual masses move around, because of the velocities that they have, even the center of mass will move around, it will shift around. So the center of mass is going to have a location, a velocity, and an acceleration. And let us also define those things. So let us say that let the center of mass have a position r center of mass, a velocity V center of mass and an acceleration A center of mass with respect to the origin of the coordinate system. Now what I want to do is, instead of analyzing these masses from this origin, I want to jump onto the center of mass. I want to sit on the center of mass, move along with the center of mass in whatever way it's moving. So now my velocity will be V center of mass and the acceleration will be A center of mass, and the place where I am in that three-dimensional coordinate system will be R center of mass. But from my own viewpoint, I will always be at the origin, because now I am keeping my coordinate system fixed to the center of mass. So this x, y, z is a different coordinate system. I'm going to create a different coordinate system, maybe x prime, y prime, z prime, that will always be centered at the center of mass. So I will always be at the origin of that coordinate system, and I will have a certain velocity, a certain acceleration with respect to this origin here, which I may call O. But from my own viewpoint, my velocity and my acceleration will be 0, because the observer always feels that the observer is at rest. And if I'm standing on the center of mass and if I'm analyzing all these objects, I might even want to apply pseudo forces on all these objects, because on all these masses m1, m2, m3, m4, etc., because I will be accelerating, and an accelerating observer should apply pseudo forces. Okay, so that's a general overview of what we are going to do. Now let us try to find out something tangible. Let's go here and find, now in the center of mass frame, suppose I want to find out the first moments of all the masses. So let me say that I am trying to find out A, the first moments of all the masses about the center of mass. So you know how to find out the first moment. I have to figure out how much the mass is, that's m1, m2, m3, m4, or any of the masses that I'm interested in, and I have to figure out what is the location of that mass. So I should use maybe r1, r2, r3, r4, and I should find the location from a certain point. So if I'm trying to find out the first moment about the center of mass, all the positions should be found with respect to the center of mass. So I should be first of all finding out what is r1. So therefore r1 with respect to center of mass, and that will be r1 minus r center of mass. Similarly, you will have r2 with respect to center of mass as r2 minus r center of mass, and in the same manner you can keep on going, and you will get maybe rn of the center of mass for the nth particle, and that will be rn minus r center of mass. And now let us try to find out the first moment of first moments of all the masses. So I have to find out summation of, so therefore summation of mi ri with respect to center of mass, and this entire term will look like summation of mi, and you will have ri minus r center of mass, where all I am trying to say is that this term is in fact m1 into r1 minus r center of mass, then plus m2 into r2 minus r center of mass, plus m3 into r3 minus r center of mass, and so on. So I will get n terms in this entire expression, and I am omitting the I is equal to 1 to I is equal to n thing here, because I just want to keep it readable. And then after that what will happen is you see that there will be summation of mi ri minus summation of mi r center of mass. So what I can do is, first I can open up this bracket, and opening up of this bracket will give me two terms. So I will have summation of mi ri minus mi into r center of mass, that entire term. And what this means is that there are n terms like this in addition, and when I've got n terms in addition like this, it doesn't matter the order in which I add up. So what I do is I club all the first terms together, and that is this first term here, and I club all the second terms together, and that's the second term here. Now this term, fine, I will actually keep it like that. This term, you see, I have got summation of mi r center of mass. So here inside this expression, inside this summation, I have got terms like m1 r center of mass plus m2 r center of mass plus m3 r center of mass, and so on, and up to n masses, right? Mn r center of mass. And what I'm going to do is, if I've got an expression like this, I can probably take r center of mass common. So this entire expression is now going to give me summation of mi ri minus r center of mass times summation of mi. And I know what is r center of mass. We have found out the formula for the position of center of mass at the starting of this chapter, and so I have got summation of mi ri, and r center of mass is summation of mi ri divided by summation of mi, and there is a summation of mi here, and after this it is trivial to see that this entire expression is going to give you a 0. So what can we say? We can say that, so therefore the conclusion that we can draw from this exercise is that in the centroidal frame, or the center of mass frame, so sometimes the center of mass frame is referred to as the centroidal frame in certain books, so you should be okay with the terminology. So in the centroidal frame, the first moment, the total first moments or moment of all the masses of all the particle masses is 0. So if you are standing in the center of mass frame, and if at all you have a requirement to find out this summation of mi times ri with respect to the center of mass, you can immediately say that this term is going to be 0. So we will see how it is used, right? But please keep in mind that this is going to be 0. Okay. So this is the first moments of all the masses about center of mass. Next, let's try to figure out what is the total linear momentum of all the masses about the center of mass. So let's go for a B part. Total linear momentum in center of mass frame. So in the center of mass frame, if I have to find out the total linear momentum of all the particles, then first I should be able to find out the velocities of all the particles in the center of mass frame. So to that end, what I do is first find out v1, the velocity of first particle in the center of mass frame, and that is v1 minus v center of mass. v2 in the center of mass frame is v2 minus v center of mass, and similarly this scheme will go on till I find out what is vn, the velocity of nth particle in the center of mass frame, and that will be vn minus v center of mass. This is the velocity of nth particle in the center of mass frame. Now if I want to find out the total linear momentum in the center of mass frame, all I have to do is find out what is summation of, so therefore summation of mi vi, but in the center of mass frame, and if I just add up all those terms, I'm going to get the total linear momentum. So what's that? You can just insert Vi minus V center of mass for this term. So you're going to get summation of Mi times Vi minus V center of mass. Now I think you know the drill by now. So what I have to do is first of all open up this bracket. So I will get terms like Mi Vi and Mi into V center of mass, and there will be two terms for each of the summation terms. So there is a sum here that's for n terms, and each of those n terms has got two terms within it. So I have got two n terms to add. I club the first term of each bracket and I get summation of Mi Vi minus, and then I club up all the second terms of all the brackets, summation of Mi V center of mass, and this will give me, I will keep the first term as it is, summation of Mi Vi minus, because here I have got n terms and each of those terms has got a V center of mass in it. I can take that term common and I'm going to get V center of mass times summation of Mi. And in the next step you understand what is to be done. Summation of Mi Vi minus V center of mass. Now you know this is summation of Mi Vi divided by summation of Mi. We have found that out earlier, and there is a summation of Mi finally. So now you know that these two terms here will go off, and what you're going to end up with in the next expression is 0. So all that is equal to 0. And that is a very interesting result. Now this result shows you that the total linear momentum in the center of mass frame should be 0. So therefore, total linear momentum in the center of mass frame or the centroidal frame is 0. Now how is it useful? It's useful in analyzing spring block systems especially. So let's say there is a spring block system. You've got a small m and then you've got a spring through which the small m is joined to a big M, like that. And at some moment small m is moving with some velocity v1 in the forward direction, big M is moving with some velocity v2 in the forward direction, and center of mass is moving in some manner. We can find out the velocity of center of mass. And this is if we are analyzing the system in the ground frame. But then what happens if you jump to the center of mass frame? So let's say the center of mass is somewhere here, that cross, and suppose you jump over to the center of mass frame. Now what this observer will see is that these two masses have velocities first of all in the opposite direction. So if this mass big M has got a velocity in the rightward direction v0, then the other one, or maybe v big M, let us say v big M, then the smaller one will have a velocity in the opposite direction, that will be v small m, such that the total linear momentum should be 0, which means the momentum of this mass in the leftward direction is equal to the momentum of this mass in the rightward direction. And you can say small m times big V with a small m subscript. So what I'm doing is this symbol I'm trying to write it as huge, showing you that if this mass is small, the velocity should be big, and if the mass is big, then the velocity should be small. And that is if you are standing in the center of mass frame. So in the center of mass frame, if this is true, then you can say that even the displacements have to be in that specific ratio. If the velocities are in the inverse ratio of the masses, then even the displacements will be in the inverse ratio of the masses. So this mass will suffer a greater displacement and this mass will suffer a smaller displacement in the center of mass frame. So you analyze the system in the center of mass frame and then you transfer everything back to the ground frame, because you know the velocity and the acceleration and the location of the center of mass at all times. So this property makes it very easier to solve all the problems in the center of mass frame. And having solved these kind of problems, now you have the theoretical idea of why is it helpful, or why was it really helpful, or why did we go into the center of mass frame at all? Because we knew this, even though not mathematically perhaps, but intuitively we had an idea of what's going to happen. Now you have maths to back up your intuition. Then final property C, which is of course, as you would have guessed, about accelerations, but it's not really about accelerations per se, because what I'm going to talk about is not going to be useful in this chapter, but it's going to be useful in the next chapter and in some specific problems. But then you should know about this property, because in those specific problems where it's useful, it is very useful. So let's say, what about the total pseudo forces and their torque about the center of mass? So torque of pseudo forces, and those pseudo forces have to be applied in the center of mass frame, because you can apply pseudo force whenever you are in an accelerating frame. So I'm just specifying that these forces, or the result that I'm going to talk about, is not for the pseudo forces applied from any accelerating frame. They have to be applied in the center of mass accelerating frame, and the torque has to be calculated about the center of mass. Torque of pseudo forces about the center of mass. So what do? So let's say that there is a center of mass here somewhere. This black dot is the center of mass, which is moving with some acceleration, a center of mass, in 3 dimensions. So this black dot is the center of mass, moving with some acceleration, a center of mass, in 3 dimensions. And of course, this is the center of mass of a n particle system, of which maybe the first particle is here somewhere. Now on this first particle, m1, there may be a number of forces, a number of real forces I mean, and we will draw all the real forces here. But if we are looking at it from the center of mass frame, then we are also going to draw a pseudo force that's going to be pointed opposite to the acceleration of center of mass, because the observer is standing on the center of mass here. So this observer will apply a pseudo force in exactly the reverse direction, and that pseudo force will be m1 times acceleration of center of mass. There is going to be another particle somewhere here, maybe that was the second particle, m2, and this observer is going to apply a pseudo force on this guy m2 also, that is probably in the reverse direction. So this is m2 times a center of mass, and so on. And this will happen for all the n particles which we have in the 3D region, which make up the system whose center of mass is this guy, So I'm just talking about those n particles here. Now this first one, first mass, is at some r1 with respect to center of mass. That's the location of m1 with respect to the center of mass. Now the location of m2 with respect to the center of mass here will be this vector, r2 with respect to the center of mass, and so on. So I can do this for all the n particles that are there in that 3D region. I don't have to really do, I just want to show you for 2 of them so that you know how it works. Now I think we haven't learned torque formally, but then I think you have a basic idea of how to find out the torque of a force about a point, and that's r cross f. So if you have a torque, if you have to find out the torque of a force F applied, now the force F is applied at a point whose location is R with respect to some point O, and I should put 2 commas here, one here and the other here. So I mean to say that this is an auxiliary thing here. So torque of a force F about the point O is R cross F. So the torque of a force F about the point O is R cross F if this F is applied at a location R with respect to this point O. So therefore I can say torque of all pseudo forces about center of mass. So let's try to calculate that, and that will be let me find out that by adding up all the R cross F terms. So what do I have? I will have R of ith particle with respect to the center of mass. So Ri with respect to the center of mass cross the pseudo force that is acting on the ith mass will be Mi times A center of mass. Mi times A center of mass. So R cross F, if I'm only talking about the torque of pseudo forces. So how can I figure out what this guy is? So what I should do is, first of all, write down terms in place of Ri center of mass. So I know that Ri center of mass is going to be R of ith particle minus R of center of mass, and that is crossed with Mi times A center of mass. In fact, I don't even have to do that. You will see that we have learned that property. It will make everything very simple. So what you do is this. You realize that this guy Mi is a scalar. Now this scalar multiplied by this vector A center of mass is going to have the effect of scaling this vector. So if Mi is say 3 times, if say Mi is 3, then it will give you a new vector which will be 3 times the acceleration of center of mass vector. That's all. So this is a scaling factor. Now this scaling factor, whether I keep it with this vector, the A center of mass vector, or I keep that scaling factor with the R vector, or whether I take this outside the bracket, it shouldn't matter at all. So what I do is, instead of keeping it with the A vector, I keep the scaling factor with the R vector here. So in the next step, what I'm going to do is, and let me do that in a different color because it's important. What I do is I play around with some vector properties and I say this is Mi Ri with respect to the center of mass cross A center of mass. So what I've done is I've taken this scalar number here and I've put it with this Ri center of mass. Now why do I do that? Now the reason I do that is when I write out this summation in that expanded form, I will have M1 R1 center of mass cross A center of mass. So let me show you that also. So when I write this one in expanded form, I'm going to get M1 R1 with respect to center of mass cross acceleration of center of mass plus, because of this summation I'm going to get a plus, then I'm going to get M2 into R2 center of mass cross A center of mass plus, then I will have M3 times R3 center of mass cross A center of mass and so on, and plus, of course, this series will go on and there will be n terms and so on. So now you know that there is a distributive property of cross product. So if you have vectors C plus D and you're trying to take their cross with another vector E, then I can rewrite this as simply C cross E plus D cross E. This is the distributive property of cross product, and I see that distributive property is what is at play here. You've got this vector A center of mass that is crossed with this guy, that is also crossed with this guy, that is also crossed with this guy. So perhaps what I have here is a sort of term that looks like summation of, and I'm not going to write that entire bracket individually term by term, so I'm just going to write this bracket which will have this term and this term and this term in terms of a summation. So maybe summation of mi ri with respect to the center of mass cross acceleration of center of mass. So this is what I will write for this entire term, and this is one vector which I will get by adding up all those inside the bracket vectors. So I could have really just opened up the bracket like this, or I could have added up C and D really if I knew what C was and what D was, and then that vector sum could have been used to cross it with E, right? So I could have done that. So here what I do is I try to figure out what this is, and we have done that. You go to result A and you see that A result says that summation of mi ri with respect to center of mass is going to be 0. So what I do is, instead of opening up the bracket here and instead of doing this term by term by term, what I do is I just take that acceleration of center of mass common. I get a huge summation inside the bracket like this. This is the C plus D bracket part, and this term is 0. So when you have 0 cross something, you are going to get a 0. So therefore this entire term is going to be 0. And so therefore now I know that torque of all the pseudo forces about center of mass is going to be 0. And of course those pseudo forces have to be applied in the center of mass frame. So I cannot go to some other frame, apply pseudo forces and try to find the torque of all those about the center. No, I have to stand in the center of mass frame, apply the appropriate pseudo force, then try to find out their torque about the center of mass, and that will be 0. Now where is this useful? This will be useful primarily in the next chapter for us, because when we are talking about angular momentum, you will see that if the net torque about a point is 0, then the angular momentum about that point can be conserved. Now if you stand in the center of mass frame and you are trying to analyze a system, and if the center of mass is accelerating, then you will end up applying a pseudo force. And then you will ask yourself whether the torque of all those pseudo forces about the center of mass is 0 or not. So this is a proof of that fact, that the torque of all those pseudo forces which you have applied by standing in the center of mass frame is 0 about the center of mass itself, and you can still try to conserve angular momentum about the center of mass if there are no other torques. So huge words, but then just keep in mind that there is a property like this. So let me just say, so therefore torque of all the pseudo forces applied in the center of mass frame about the center of mass itself is 0, which means they will not trouble you if you are trying to conserve angular momentum about the center of mass. Then the only forces which may try to trouble you will be external forces acting on the masses. So not very helpful in this chapter, but because we are doing it here for the center of mass frame, let us do this also for the sake of completeness.